Good day. Together with my partner, GC Ramirez Jaime, are here to talk about the topic of antennas and wave propagation. Topics covered in Chapter 14. First, antenna fundamentals. Second, common antenna types. Third, radio wave propagations. In wireless communication systems, an RF signal generated by a transmitter is sent into a free space and eventually picked up by a receiver. The interface between the transmitter and the free space and between free space and the receiver is the antenna. The incredible variety of antenna types used in the radio communications are all based on a few key concepts. This chapter introduces all the most popular and widely used antennas in HF, VHF, and UHF applications. Also discussed are the characteristics of free space and its ability to propagate signals over long distance, a study of wave propagations, how radio signals are affected by the earth and the space in moving from transmitting antenna to receiving antenna, is critically to understanding how to ensure reliable communications over the desired distance of specific frequencies. Antenna fundamentals. The interface between the transmitter and the free space and between free space and receiver is the antenna. At the transmitting end, the antenna converts the transmitter RF power into electromagnetic signals. At the receiving end, an antenna picks up electromagnetic signals and converts them into signals for the receiver. Radio waves. A radio signal is called an electromagnetic wave because it is made up of both electric and magnetic fields. Whenever voltage is applied to the antenna, an electric field is set up. This voltage causes current to flow in the antenna, producing a magnetic field. These fields are emitted from the antenna and propagate through space at the speed of light. Radio waves, magnetic fields. A magnetic field is an invisible force field created by magnet. An antenna is a type of electromagnet. A magnetic field is generated around the conductor when the current flows through it. As the strength direction of the magnetic field depend upon the magnitude and direction of the current flow. The SI unit of magnetic field strength is ampere turns per meter. This figure shows magnetic field around a current carrying a conductor. When a current flows through a conductor, it generates a magnetic field around it in the form of concentric circles. The direction of a magnetic field is determined by the right-hand rule, where curling your fingers around the wire follows the field lines if the thumb points in the direction of the current. The field strength depends on the current and the distance from the conductor. Radio waves, electric field. An electric field is an invisible force field produced by the presence of potential difference between two conductors. For example, an electric field is produced between the plates of the charged capacitor. An electric field exists between any 2 points across which a potential difference exists. The SI unit for electric field strength is volts per ampere. Permittivity is the dielectric constant of a material between the two conductors. This figure shows electric field across the plates of a capacitor, which have shortage of electrons. Capacitor plates exist electrons, electric field lines of a force with the formula of E equals Q over 4 pi epsilon D squared. The electric field across the plates of a capacitor is created when opposite charges accumulate on its plates due to a voltage difference. This field is uniform and points from the positively charged plate to the negatively charged plate. Radio waves, magnetic and electric fields in a transmission line. At any given time in two-wire transmission line, the wire have opposite polarities. During one half cycle of the AC input, one wire is positive and other is negative. During the negative half cycle, the polarity reverses. The direction of the electric field between the wires reverses 1 per cycle. The direction of the current flow in one wire is always opposite than in the other wire. Therefore, the magnetic fields combine. A transmission line is made up of a conductor or conductors. Transmission line do not radiate signals efficiently. The closeness of the conductors keep the electric field concentrated in the transmission line dielectric. The magnetic field mostly cancel one another. The electric and the magnetic fields don't extend outward from the transmission line, but the small amount of radiation that does occur extremely inefficient. This figure shows in picture A magnetic and electric fields around a transmission line, in picture B electric field, in picture C magnetic fields. Antenna operation, the nature of an antenna. A magnetic fields no longer cancel, they now aid one another. The electric field spreads out from a conductor to conductor. Optimum radiation occurs if the segment of transmission wire converted into an antenna is 1/4 wavelength long at operating frequency. This makes an antenna that is 1/2 wavelength long. This figure shows that converting a transmission line into an antenna. In picture A, an open transmission line rotates a little. In picture B, bending the open transmission line at the right angles creates an efficient radiation. Antenna operation. The ratio of electric field strength of a radiated wave to the magnetic field strength is a constant and is called the impedance of space, or the wave impedance. The electric and the magnetic fields produced by the antenna are the right angles to one another and are both perpendicular to the direction of propagation of the wave. Antennas produce two sets of fields, the near field and the far field. The near field describes the region directly around the antenna where the electric and the magnetic fields are distinct. The far field is approximately 10 wavelengths from the antenna. It is the radio wave with a composite electric and magnetic fields. Polarization refers to the orientation of magnetic and electric fields with respect to the Earth. Antenna reciprocity. Antenna reciprocity means that the characteristics and performance of an antenna are the same whether the antenna is radiating or intercepting an electromagnetic signal. A transmitting antenna takes a voltage from the transmitter and converts into an electromagnetic signal. A receiving antenna has a voltage induced into it by the electromagnetic signal that passes across it. The basic antenna. An antenna can be length of a wire, a metal rod, or a piece of tubing. Antennas radiate most effectively when their length is directly related to the wavelength of the transmitted signals. Most antennas have a length that is some fractions of a wavelength. 1/2 and 1/4 wavelengths are most common. Common antenna types. The dipole antenna. One of the most widely used antenna types is the half-wave dipole. The half-wave dipole, also called a doublet, is formally known as the Hertz antenna. A dipole antenna is a two pieces of wire, rod, or tubing that are 1/4 wavelength long at the operating resonant frequency. Wire dipoles are supported with glass, ceramic, or plastic insulators at the end and middle. This figure shows that the dipole antenna, which have 73 ohms resistance in the middle and have an antenna conductor and a transmission line. The dipole has an impedance of 73 ohms at its center, which is the radiation resistance. An antenna is a frequency-sensitive device. To get the dipole to resonate the frequency of operations, the physical length must be shorter than the 1/2 wavelength computed by lambda equals 492 over frequency. Actual length is related to the ratio of length or diameter. Conductor shape Q, the dielectric when the material is other than air, and condition known as end effect. End effect is a phenomenon caused by any support insulators used at the ends of the wire antenna and has the effect of adding capacitance to the end of each wire. The actual antenna length is only about 95% of the computed length. If a dipole is used at a frequency different from its design frequency, the SWR rises and power is lost. Antenna Q and bandwidth. The bandwidth of an antenna is determined by the frequency of operations and the Q of the antenna according to the relationship bandwidth equals frequency over Q. The higher the Q, the narrower the bandwidth. For an antenna, low Q and the wider bandwidth are desirable so that the antenna can operate over a wider range of frequencies with a reasonable SWR. In general, any SWR below 2.1 is considered good in a particular antenna network. The Q and thus the bandwidth of an antenna are determined by the ratio of the length of the conductor to the diameter of the conductor. Bandwidth is sometimes expressed as the percentage of the resonant frequency of the antenna. A small percentage means a higher Q, and a narrower bandwidth means a lower percentage. Conical antennas. A common way to increase bandwidth is to use a version of dipole antenna known as the conical antenna. The center radiation resistance of conical antenna is much higher than 73 ohms, usually found when straight wire or tubing conductors are used. The primary advantage of conical antennas is their tremendous bandwidth. They can be maintained a constant impedance and gain over a 4.1 frequency range. Dipole polarization. Most half-wave dipole antennas are mounted horizontally to the earth. This makes the electric field horizontal to the earth and the antenna is horizontally polarized. Horizontal mounting is preferred at the lower frequencies because the physical constructions, mounting, and support are easier. The mounting makes it easier to attach the transmission line and route it to the transmitter or receiver. Radiation pattern and directivity. The radiation pattern of any antenna is the shape of the electromagnetic energy radiated from or received by the antenna. Most antennas have directional characteristics that cause them to radiate or receive energy in a specific direction. The radiation is concentrated in a pattern that has a recognizable geometric shape. The measure of an antenna's directivity is beam width, the angle of the radiation pattern over which is a transmitter energy is directed or received. This figure shows us the three-dimensional pattern of a half-wave dipole, which have a lambda over 2 dipole. Antenna gain. The directional antenna can radiate more power in a given direction than a non-directional antenna. In this favored direction, it acts as if it had gain. Antenna gain of this type is expressed as the ratio of the effective radiated output power P out to the input power Pin. Effective radiated power is the actual power that would have to be radiated by a reference antenna, usually a non-directional or dipole antenna, to produce the same signal strength at the receiver as the actual antenna produces. The power radiated by an antenna with directivity and therefore gain is called the effective radiated power, ERP. ERP equals E sub P times P sub T. Folded dipole. A popular variation of the half-wave dipole is the folded dipole. The folded dipole is also one half wavelength long. It consists of two parallel conductors connected at the ends with one side open at the center for connections to transmission line. The impedance of this antenna is 300 ohms. Folded dipoles usually offer greater bandwidth than standard dipoles. The folded dipole is an effective low-cost antenna that can be used for transmitting and receiving. This figure shows that folded dipole. In picture A, basic configuration which have a 300 ohms twin lead and 300 ohms impedance and have a lambda over 2 and has a spacing. In picture B, constructions with a twin lead. Same. Yeah po siya. But wires twisted and soldered. Grounded ground plane vertical antenna. The 1/4 wavelength vertical antenna, also called a Marconi antenna, is widely used. It is similar in operations to a vertically mounted dipole antenna. The Marconi antenna offers major advantages because it is half the length of the dipole antenna. Vertical polarization and omnidirectional characteristic can be achieved using a 1/4 wavelength vertical radiator. This antenna is called a Marconi or ground plane antenna. It is usually fed with a coaxial cable. The center conductor is connected to the vertical radiator and the shield is connected to earth ground. The earth then acts as a type of electrical mirror, providing the 1/4 wavelength, making it equivalent to a vertical dipole. This figure shows a ground plane antenna. In picture A, 1/4 wavelength vertical antenna, and picture B using a radial as a ground plane. Ground plane, radials, and counterpoise. When a good electrical connection to the earth has been made, the earth becomes what is known as the ground plane. If a ground plane cannot be made to earth, an artificial ground can be constructed of a several 1/4 wavelength wires laid horizontally on the ground or buried in the earth. These horizontal wires at the base of the antenna are called radials, and the collection of radial is called counterpoise. Antenna length. For many applications with a portable or mobile equipment, it is not possible to make an antenna a full 1/4 wavelength long. To overcome this problem, shorter antennas are used and lump electrical components are added to compensate for the shortening. The practical effect of this design is decreased inductance. The antenna no longer resonates at the desired operating frequencies but a higher frequency. To compensate for this, a series inductor called a loading coil is connected in a series with the antenna coil. The loading coil brings the antenna back into resonance at the desired frequency. This figure shows that using a base leading coil is to increase effective antenna length, which is have a loading coil, a vertical antenna less than lambda over 4, and a coaxial feed. Directivity refers to antenna ability to send or receive signals over a narrow horizontal directional range. The physical orientation of the antenna gives it a high directional response or directivity curve. A directional antenna eliminates interference from the other signals being received from all directions other than the desired signal. A highly directional antenna acts as a type of a filter to provide selectivity. Directional antennas provide a greater efficiency of power transmission. Directivity, because if this focuses the power, causes the antenna to exhibit gain, which is one form of application. To create an antenna with a directivity and gain, two or more antenna elements are combined to form an array. Two basic types of antenna arrays are used to achieve gain and directivity. First, parasitic arrays. Second, driven arrays. A parasitic array consists of a basic antenna connected to a transmission line plus one or more additional conductors that are not connected to the transmission line. These extra conductors are referred to as parasitic elements, and the antenna is called a driven element. A Yagi antenna is made up of a driven element and one or more parasitic elements. A driven array is an antenna that has two or more driven elements. Each element receives RF energy from the transmission line. Different arrangements of the elements produce different degrees of directivity and gain. The three basic types of driven arrays are the collinear and broadside and the end fire. The fourth type is the wide bandwidth lag periodic antenna. Collinear antenna. Collinear antennas usually consist of two or more half-wave dipoles mounted end-to-end. Collinear antennas typically use half-wave sections separated by certain quarter-wave matching stubs, which ensure that the signal rejected by each half wave section are in phase. Collinear antennas are generally used only on VHF and the UHF bands because their length becomes prohibited at the lower frequencies. Broadside antenna. A broadside array is a stacked collinear antenna consisting of half-wave dipoles spaced from one another by one-half wavelengths. This antenna produces a highly directional radiation pattern that is broadside or perpendicular to the plane of the array. The broadside antenna is bidirectional in radiation, but the radiation pattern have a very narrow beam width and high gain. End-fire antenna. The end-fire array used to half-wave dipoles spaced one-half wavelength apart. The end-fire array has a bidirectional radiation pattern, but with a narrower beam width and a lower gain. The radiation is the plane of the driving elements. A highly unidirectional antenna can be created careful selection of the optimal number of elements with a appropriately related spacing. Log periodic antennas. A special type of driving array is the wide bandwidth log periodic antenna. The lengths of the driving elements vary from a long, short, or related logarithmically. The spacing is also variable. The great advantage of the log periodic antenna over a Yagi or the other array is it is very wide bandwidth. The driving impedance is constant over this range. Most TV antennas in use today are the log periodic variety so that they can provide high gain and directivity on both VHF and UHF TV channels. Impedance matching. One of the most critical aspects of any antenna system is ensuring maximum power transfer from the transmitter to the antenna when the characteristic impedance of the transmission line matches the output impedance of the transmitter and the impedance of the antenna. The SWR will be 1-1. When the SWR is 1-1, maximum power transfer will take place. A Q section or matching stub is a 1/4 wavelength of coaxial or balanced transmission line of a specific impedance that is connected between a load and a source, and it is used to match impedances. A balloon is a transformer used to match impedances. An antenna tuner is variable inductor, one or more variable capacitor or combination of these components connected in a various.
Good day everyone. Today, I'll be discussing about radio wave propagation. So what is radio wave propagation? Well, radio wave propagation is the movement of electromagnetic waves through a medium or space. It includes how waves travel, reflect, diffract, and refract. So before I'll be discussing the radio wave propagation, I'll be explaining first what is happening in communication channel. In this communication channel, we have transmitter circuit which is giving transmitting signal to the transmitting antenna, and then transmitting antenna that radiates electromagnetic waves. And these electromagnetic waves that is propagating along the propagation path is getting received by the receiving antenna, and this signal is given to the receiver. So basically, when it propagates in the channel, the way it propagates is called propagation mode. So in this video, I'll be explaining different types of modes of propagation. And in this video, I'll be explaining basic details regarding the different modes of propagation. So these are the different modes of propagation: ground wave propagation, tropospheric propagation, ionospheric propagation, and line of sight propagation. And let's proceed to the diagram which every modes will be explained. This is the Earth's surface. This is the trans- transmitter antenna, and the receiver antenna. First, I will be explaining ground wave propagation. Ground wave propagation works when the transmitting antenna sends signal to the receiving antenna through the ground. Again, when the transmitting antenna sends signals to the receiving antenna through the ground. So the electromagnetic waves propagates through the ground. So this is called ground wave propagation. And next is the tropospheric propagation. Tropospheric layer is 16 kilometers above the ground of the Earth's surface. Tropospheric propagation works when the transmitting antenna sends signal to the tropospheric layer, and then after scattering, those signals will reflect back to the Earth's surface, and the receiving antenna receive those signals. Again, when the transmitting antenna sends signal to the tropospheric layer, and those signals will reflect back to the Earth's surface, and the receiving antenna will receive those signals. So this is called tropospheric propagation. Here, there are two happenings, which are reflection and scattering. Next is the ionospheric layer. Just like the tropospheric propagation, when the transmitting antenna sends signal to the ionospheric layer, and then those signals reflect back to the receiving antenna, this is called ionospheric layer propagation. I mean, combining these two, propagation is referred to as sky wave propagation. And lastly is the line of sight propagation. Line of sight propagation works when the transmitting antenna sends those signals directly to the receiving antenna with a straight path. So the electromagnetic waves propagates through a straight path. Unlike to the ground wave propagation, the electromagnetic waves propagates along to the propagation path through the ground, while the transmitting antenna, while the line of sight propagation, I mean, when the transmitting antenna sends signals to the receiving antenna, it propagates through a straight path. So
The signals is sent directly to the receiving antenna.